Thank you for joining me today. This is our fourth session on the subject of computer architecture, and this time we will be looking at some of the future memory technologies that we might be seeing emerge in the next 5 to 15 years. So, organization for this talk, like last talk, will work by levels. Level 1 being the most accessible subjects, all the way to level 3, where we go into more technical details. As usual, this is recorded, so feel free to recheck level 3 if you didn't understand the first time. So, what we'll be exploring today, we'll start by a quick overview of FRAM, then we'll look into another technology called MRAM. There are different types of MRAM. Today we'll be looking at STT-MRAM and SOT-MRAM. Then we'll look a little bit at a proposed 3D stacking technology called Next that was recently unveiled by TSMC and how memory is portrayed in that. And afterwards, in our last part, we'll be looking at an interesting mass cooled storage solutions that we have been seeing emerge recently and is becoming more and more prominent and an interesting solution for long-term storage. Let's get right into it. All of the topics we'll be covering here are related to non-volatile memory. So non-volatile memory is a memory that even when unplugged, when the memory cells are not powered, retain their data, retain their state, and so you can use it for storage between um, two work sessions in your computer. So let's get right into it. FRAM. FRAM, also called ferroelectric RAM, is a type of memory that has been presented in the mid 90s and has gained a little bit of traction in the beginning of the 2000s, but has lost that traction in recent years. Anyway, some proponents of FRAM say it does have a future, and so we're still going to look into it today. So, how does it actually work? Well, in this case, the memory cell looks a little bit like the DRAM, except you have this additional ferroelectric capacitor and this drive line. Why is this? Because the main idea of FRAM is that you will adjust the polarization of your ferroelectric crystal structure by polarizing it in one way or the other. So basically, you've got a free a free atom that can move inside the structure, and based on where it is in the structure, how the structure is polarized, you have a different dielectric constant. And this difference in the dielectric constant results in a change in the capacitance when you make a current flow through this resistor. So basically, when I'll make a current through this resistor, if it's positively polarized, then I will have R0 as no QR, sorry, QR as my capacitance, and if it's um, negatively polarized, which translates to a 1, I will have minus Q0, basically negative capacitance. And so for a given voltage, I'll, I'll I will I will indirectly measure the capacitance on this charge. This is quite interesting because unlike the DRAM cells where we're storing charge, here we're basically storing the information as a polarization of a stable crystal. And so this does not leak charge because it is not charged by definition, and also is rather stable. So there's also no need to refresh it because it doesn't lose charge simply over time while idle. Now, how does this actually work? Well, let's say we wanted to write something to our FRAM SAM. Then we would activate or not the value. We would activate the value on our drive line that is hidden by my menu here. And then based on if we wanted to write a 1 or a 0, we would activate or not our bit line. And so the value of our bit line would then, if I wanted to write a 0, I would put a 0 on my bit line. And if I wanted to write a 1, then I would put a 1 on my bit line. And this is how I would I would change the polarization of my ferroelectric capacitor. Now, let's see how this actually works for reading. Well, at the beginning, I'll have an idle state. So this is basically when it's doing nothing, I'll have 0, 0, and 0 on all lines. So no, I'm not applying any voltage to it. Now, to read, I'm actually going to set my bit line to floating, which means floating means that if I don't explicitly drive it, which means apply a current, either by connecting it to the ground or connecting it to my power supply VDD. If I leave it floating, then based on the value of the lines it's connected to, it will change. I would change the voltage on it. So if I have a high capacitance, which is a 0, this means that I have a high capacity, and so when I'll drive my line here, since I have a high capacity, it'll take some time for the capacity to rise. And since I'm sampling really fast, I'll basically perceive that there aren't any charges. And if I have a 1 written, which means I have a low capacity, then the voltage will simply flow through. And so I have a voltage. I'll read the voltage as a result of basically the base capacity of my cell. So basically here I would read a 0, and here I would read a 1. Also, the problem with this is that I said that to write we would drive the line, but it's quite similar to the process of reading. And what happens in practice is that when we do the reading process, it's a destructive process where we slightly alter the configuration of our crystal structure. And so it is considered a destructive process. And so after every read, like in DRAM, we would want to rewrite the value that we read for it not to lose its state. So there's another big problem with FRAM, and this is one of the reason be, be one of the main reason it hasn't reached a wider audience and a wider adoption is that the voltage you need to apply to polarize your crystal is actually a rather high voltage. So we add a structure called an electron pump, which basically pumps voltages until it reaches a certain higher voltage, let's say 15 volts, and then it will discharge it all in one go in order to reliably write the polarization to your crystal. Now, this requires additional logic and additional time to do the pumping. So this because of this, an FRAM cell is actually rather slow and can be rather energy inefficient. It's not the memory cell itself, it's the process of writing and reading. Also, the scaling of the memory cell is dependent on the size of your ferromagnetic capacitor. And in this case, it's dependent on the size of the ferroelectric film inside the capacitor. And unfortunately, that does not scale very well. And so we basically have memory cells that don't scale. So when we want to scale it down to our, say, 7 nanometer process, unfortunately, this technology isn't able to reach those requirements. Now, okay, so we pushed FRAM out of the way. Maybe in the future there will be new research enhancements, but this is at least the perceived state of it. Let's go to MRAM. So let's start simple. MRAM. MRAM, also called magnetoresistive RAM. We'll go into detail on why we use these terms later. Works by storing a value as a resistance. So based on the value of the measured resistance, you would either have a logical high bit or a logical low bit. This, like in DRAM, is amplified via a sense amplifier, and then the resulting thing is interpreted as either 0 or 1. So far, so simple. Now let's get into things a little bit deeper into things in level 2. So an interesting concept that we will be manipulating for MRAM is the idea of current polarization. Basically, your electrons can be polarized with spins. So you can have a 1.5 spin, which we will call for our purposes positive, and a minus 1.5 spin, which we call negative. We consider these as this is the polarization of an electron. So in normal metal, you have the same probability of having polarization, positive polarized electrons and negative polarized electrons. Now that is not true for ferromagnetic structures, um, ferroelectric metals, where you have a higher probability of having a certain type of polarization for your current. And we will use this principle for MRAM. So let's say that we have 3 layers of a material. One has a positive polarization, one is just a classic film, that's a classic metal, and one has a negative polarization. The electrons with the same polarization as the structure, as our metal here, will pass through, but when they reach a metal that is negatively polarized or polarized where their polarization is not parallel to the electron's polarization, then they will be filtered out, to put it in simple terms. And so less of them will pass through. This is true for both polarization. And a result of less electrons passing through a certain structure is actually simply resistance. And here we see that if the polarization of the metal and the polarization of the electrons are parallel, there isn't any hindrance to its passing through. So how do we actually use this in practice? Well, we have 2 different metals. We'll call them layers. We have a free layer that can change its polarization, and we have a fixed layer, which is much larger, that is always polarized in the same way. And we will make a flow of electron flow through it, and based on if the 2 layers are parallel or anti-parallel, a certain amount of electrons will actually be able to pass through. So if they're parallel and my incoming electrons were also were also polarized in this manner, then I would have a big flow of electrons passing through. They wouldn't be hindered, and so I would have a resulting low resistance. But if my electrons are polarized in the same manner as here, they will not be able to pass through the anti-parallel polarized layer, and so this will be a hindrance to their flow and result in higher resistance with less electron passing through. And so, we use this. We'll say that here is our parallel state and here is our anti-parallel state. So in this case, we have our free layer that is configured anti-parallel to our fixed layer, and here we'll have them both with the same polarization. We'll take a sampling voltage, put it this one, and so I've got a question. So that's a gate. Unfortunately, I do not see what you mean by a gate. I'll, I'll do questions at the end. So here I have my sampling voltage, and based on the configurations of my layers, the resulting voltage flow will be measured with higher low resistance, and so the amount of electrons measured will give me a logical value. So this would be, for example, logical low, and this would be a logical high. In this case, I would have more electrons, and in this case, I'll have less electrons. And so you can see that I have a hysteresis loop where I can go from anti-parallel state to parallel state. Now we'll look more into detail on how we switch that polarization, and that is the fundamental difference between both types of MRAM. So the read process is the one I presented you, is something we call TMR, and the write process is actually what differentiates both MRAM types. So in the case of the SST MRAM, we use something called the spin transfer torque principle. We use the principle of spin transfer torque in order to write the polarization of our free layer. And in SOT MRAM, we use the principle of spin orbit torque to configure the polarization of our free layer. Now let's get right into it and start with SST MRAM. So spin transfer torque. The principle between spin transfer torque is if I want to write the polarization of of my free layer, say I start in a state where I have an anti-parallel configuration and I want to write it to parallel. Well, I'll start by making my flow electron go through my thick layer. So this is a thick layer, so it's really, really hard to change its polarization. But this one is a really, really smaller layer, so it's the probability of it switching polarization is much higher. And I'll put my electrons going through this one. So they're going through here, and so basically all the electrons that make it through here will be guaranteed to have this polarization. And now the electrons with this polarization are going to come into my free layer, and they're going to apply torque, and little by little they're going to change the polarization of this layer. So let's say that 100% of my layer was polarized this way. Little by little, my electrons will start pushing it this way until 100% or close to 100% of my free layer um, changes polarization, and now we have a parallel configuration. So this is the principle of writing a zero. And now for writing, if I am in the parallel configuration and I want to go through anti-parallel, then instead of coming through this side, my electrons would come through this side. And so all the electrons that will have this polarization will simply be able to flow through without much resistance. But the electrons that do not have these polarizations are actually going to be reflected in a way, and then they're gonna hit my free layer, and they're the ones that are gonna nudge it little by little until we hit an anti-parallel configuration. So how does this actually work? Say I start here with my parallel configuration. If I want to go through an anti-parallel configuration, I'm going to apply a positive voltage and make electrons flow this way. So they'll flow here, and then they'll bounce back, and then they'll change the polarization of this one. And so now I'll be in this state. So this is here. And now if I wanted to go and write a parallel configuration, my flow of electrons would be the other way around, and they'll start little by little changing the polarization here until I get into a parallel state. And this is how our hysteresis loop works, with here being the negative voltage and here being the positive voltage. And negative voltage and positive voltage, the difference in sign actually translate to a difference of direction for the flow of my electrons relative to my structure. So here this is positive and this is negative. So this is how the ST-MRAM cell looks internally. So here I have my bit line, my very classical bit line, which here I have my word line underneath. This is the one I would trigger in order to select a memory cell. And then, and this one too would need to be selected, and the result would flow through my digit line. And this is on this line that I would read the result. Now, let's go into the issues of STMRAM and the challenges that designers that or people that wish to use it are facing. The, one of the very fundamental things with SST MRAM and MRAM in general is that unlike other types of memory, we can currently scale it, which is good because it allows us to build it for smaller process nodes. The problem is that a smaller cell results in a smaller switching current, but this decrease is not linear, which means that if I actually if I use the gained area and pack as many cells as I used to in this smaller area, say I used to be able to pack 8 cells and now I can pack 32 cells. If I pack these 32 cells, then the power density would actually increase because this decrease is not linear. And so I basically now have to manage a bigger heating issue and a bigger power consumption issue per area. Now I have a couple of questions. Do you guys want me to answer them right away, or do you guys want me to answer it at the end? I think I'll answer them all at the end. I'm sorry for not answering them right away, but I feel that you might find the answers to your question in the next slides. So yeah, so now we have a problem with increased power density and so increased heat that we have to manage. So it's a drawback, definitely. Now, the problem, so we know that this increased heating is due to the nonlinear scaling of my switching current at a constant voltage. So can I reduce my switching current, which would then allow me to reduce my power consumption and so my heat? Well, we actually can. The pulse length is actually, in a way, equivalent to the current I am drawing. So basically, longer pulses means less current in a given amount of time is flowing through. The problem with that is that longer pulses also means less electrons per unit of time, which is the definition of less current. But in my case, it also means slower switching. So I can reduce the current I'm drawing, but then I would also reduce, well, sorry, I would also reduce the maximum operating frequency by making the time I need to make a write operation longer. So that's okay. I know it's slower, but lowering the current does not only impact the switching speed, it also leads to shorter data retention because I am. So we kind of have this trilemma where on one hand we would like to reduce the area, which would mean also reduce the cost. On the other hand, we have the data retention, and on the last hand, we have a higher performance. And we have to make a choice. Either we want something that will store data for a long time, but doing this, I would need to apply higher current and so higher power draw, or I want something that switches really, really fast, but then I might not be able to scale my cells as much as I want because then I have a power density per area that explodes. Or, but if I make my cells bigger, then I need more die space, and then that leads to higher costs. Appreciate the beauty of the problem. Okay, now this isn't actually all grim. STT-MRAM has interesting proprietaries, not for all types of MRAM, but it would potentially be very interesting for level 3 cache. Because level 3 cache, unlike level 1 and level 2 cache, doesn't have to be as fast. It still has to be extremely fast when compared to DRAM, but still we can spare a cycle or two. Additionally, it seems that according to some of the leading developers in this, the area needs for a standard logic cell, you actually get a sweet spot between switching rate, the current you use, and the area you need for level 3 cache. But not for DRAM because we want to have a compared to DRAM rather big cell sizes because we don't want to have a too high power draw, but these really big cell sizes means that we have really low capacity. But so we can't use it for DRAM because then we would make DRAM chips with very bad capacity. But currently we for L3 cache we use a memory that we saw last week called SRAM, and if you remembered, we said that SRAM uses a lot of space. So if we use this additional space and gave it to STT-MRAM, we might have a sweet spot. Okay, so that was STT-MRAM, and then let's look at our second MRAM type called SOT-MRAM. Also, and this works on the principle of spin-Orbit torque for transfer polarization. The idea you need to understand this is that in certain types of metals, namely heavy metals, the scattering of the polarized electrons is asymmetric. So this basically means that given a metal, you have a higher probability of positively, say, polarized electrons going to your left and a higher probability of your negatively polarized electrons going to your right. And this is what we're actually going to use. Now, say we have two current polarizations. This in one case, our electrons are going this way, and we can see that our positively polarized electrons are going to go this way. Now now we have all our positively polarized electrons ending up here. Now if I wanted to get negatively polarized electrons instead of positively polarized electrons, I would simply invert the direction of my electron flow, and because this and thanks to this, I would have negatively polarized electrons here. And so we can see it as a switch for giving us either positively polarized electrons or negatively polarized electrons. So how are you actually going to use it? Now here you might remember I have my cell, so I've got my fixed layer and my free layer, and here I've got my metal, and I'm going to switch the polarization of I'm going to switch the direction of my current flow through this heavy metal, say based on the polarization I want on my free layer. So how would this work? Well, here I have another view. So here I have my free layer, and I would have a kind of surface effect where if I have negatively polarized electrons that end up on top, then they'll come in collision with my free layer. Well, they'll go next to my free layer, and they will switch the polarization, and then the positively polarized electron will be discarded into the substrate. And if I want to, let's say, have positively polarized electron, I would simply inverse the current direction, and then my positive electrons would end up here, and my negatively polarized electrons would then be discarded into the substrate. This is a little bit abstract. Simplified analogy is having hot chocolates in the snow. So even though my snow here, which will be my analogy for my free layer, isn't directly in contact with my hot chocolate, I still have a surface effect, whereas my snow will melt due to the heat of the hot chocolate inside my cup. And this is the same idea, because we have a surface effect that will change the state of of the polarizations of my free layer. So compared to STT-MRAM, SOT-MRAM has been boasted to have a more efficient switching method, and also because it's more efficient, allow for faster switching rates. So basically, faster writing and faster reading, especially faster writing, and lower power density because I will not need to have the same amount of electrons going through for a write to make sure my write happens because of this more efficient switching method for more efficiently with the same amount of electrons changing the polarization of my fixed layer. Oh, and this also means, yeah, lower write currents. Also, apparently, I I have not found a clear justification for this, but I will assume that this is also linked to a more efficient switching method. In my trilemma, I can take off the problem of data retention, and now I'm simply left again with the problem of lower cost or higher performance. Now, on the downside, SOT-MRAM compared to STT-MRAM is that SOT-MRAM, as you might have seen from the representation we saw earlier, has a more complex memory cell design, which means that it needs more masks to be made, and so has a more expensive manufacturing process and requires slightly more area on the die per cell. Also, there is the use of heavy metals involved, which complexifies and adds an additional cost. So now let's take a step back from different memory cells and let's look a little bit at general 3D stacked memory. It's still quite early to identify a clear winner in this space, but today we'll be looking at proposal made by TSMC, which they called Next. The main idea behind Next is that the top section of your chip is used to store the memory cells. Then you have a sandwich of different layers. You have here some interconnect. Then here you have a thin layer of energy efficient logic. So this would be the logic that you would want to keep next to your memory that will not switch that much, but is still needed, for example, to select a memory line or maybe do a little bit of maintenance. For example, have your cache policy for replacements. And then underneath that, you would actually have your logic. Now, it's still unclear if this will actually be the technology that they implement in the future. But this is at least a proposal that they made. If you guys are interested, this was done at Hot Chips 31, and the video is available online. I encourage you to go see it. Okay, now let's talk a little bit about the problems that are not often addressed with 3D stacking. First, of course, there's the cost of the technology. We all know that as this manufacturing process is much more complex, the associated cost will be much higher. Also, this is a new technology, and so the stability um, of the yields isn't assured, and so lower yields also means more defects, which means more time, more manufacturing process, basically a higher cost. But there's a second problem that isn't associated as much. It's the noise. Now, you might have remembered that I talked a bit about the noise that you have inside chips. Now, that the noise that I presented was simply for planar technologies. Now, imagine if you start stacking multiple layers of transistors, the amount of noise you're going to have is going to explode. So this will be a dilemma and a new challenge that will need to be addressed. Also, there's the problem of heat. How do you manage the heat? How do you get rid of that heat? That too will need to be addressed, and that is why, in their example, TSMC specified that they were using non-volatile memory in order to discard DRAM as it is less power efficient, and also they specifically said that these internal layers were going to be low powered in order to reduce the heat issue and allow a little bit more the heat to dissipate through these higher layers. Okay, so now we've seen two technologies that, if they were implemented, would probably be implemented on die, on silicon. Now, we're addressing rather small memory capacities. And on the other hand of the spectrum, we have cold storage. So the idea with cold storage is you have very, very high capacity. You want to store a lot of data, and you don't really care as much about your access latency. You have other priorities, and one of them is capacity, and the second of them is cost. You want to store as much capacity as you can, the cheapest possible price. So let's get right into it. So you have capacity, also you have reliability, which is a major issue, and then finally you have latency, which you don't care about. But you care about the most is the cost per gigabyte. So you have two ways of reducing the cost per gigabyte. Either you can increase the capacity and keep your standard your obtain package at the same size, or you can reduce the cost per gigabit. Now, we measure the storage capacity of a device by the amount of information that it can store per square inch. So here we have three different types of technologies. We have our classical disks, HDD in red. We have NAND, which is the one that you find in your smartphones, in green. And then you have a last one in blue called LOT. Now keep in mind, all of the following charts will be expressed on a logarithmic scale. So there is a clear gap between the two. So what is a square inch for NAND? Well, NAND is an on-chip, um, is on die. So it's expressed. So when we're talking about square inch, we're actually talking about square inch of silicon, which, as you know, is limited in size. We cannot make as big dies as we want to, and also is rather expensive. Then for HDD, when we're talking about area, we're actually talking about the surface on the disk. Now, in recent technology, we're starting stacking multiple disks. And in this case, we're talking about the surface on one disk multiplied by the amount of available disks. And now LOT actually translates to linear tape open. It's an open standard for tape. Yes, exactly, tape. The thing that people used to store data on in the 60s and 70s. It's still around, and it's kicking as strong as ever. Now, when we're talking about tape, when we measure the area capacity per square inch, the square inch of tape is actually, well, the height on the tape. And generally, in the LOT standard, this is a half centimeter wide and 1,000 to 1,500 meters long. That's a lot of storage area. Now, when we actually look at what interests us, the price per gigabyte, we can clearly see that the winner is tape. The price per gigabyte has been decreasing constantly by around 10% per year since 2008. So for the past 9 years, which makes it, as you see, when compared to HDD and NAND, a very cost-effective technology. So let's go more into detail and let's talk about tape. So how does tape actually store stuff? Well, in tape, we're polarizing um, crystals, like in our a little bit like in our previous examples, and then we're taking a certain area and we're measuring the polarizations of the crystals in this area. And if the polarization is negative, then we have a negative bit cell, so this could be translated to a 0. And if we have a positive, then we have a positive pixel, and this is translated to 1. Now you can see here that my crystals aren't very, very well organized on my tape, and so I have to widen the area that I am considering for one memory cell in order to have the reliability I want. Now, if I could make my crystals better organized, closer, then I could reduce the area I need per memory cell and so increase the capacity of my tape. And what actually leads to most of the um, the ununiformity in my in my crystals is actually the this interface not being smooth. This is called the soft magnetic underlayer, and I want this interface to be as smooth as possible. Otherwise, it will disrupt my crystalline organization. So what does this actually look like? Well, here we have a cut between two different technologies, different evolution of the tape technology. And in this case, we have a very chaotic, if I dare say, um, a layer. We can see it here, and so my crystals will be all around the place. And here we have a very smooth layer, and so my crystalline organization is going to be much more uniform. And this is actually a cut. So previous technology, and so we can clearly see that my crystals are all over the place. And more recent evolution, where we have something smoother, and this smoother interface leads to better organizations on the layer above. Now, we have actually recently seen another leap in this technology. Before, we were using a process called barium ferrite to build this underlayer, and currently we're using a process that uses vacuum sputter. And here we can clearly see this is a 50 nanometer scale, and this is a 7 nanometer scale. Here we're taking a picture of a crystal organization on the top layer. You can see that this one is very, very uniform, as this one is absolutely gorgeous. And this new technology actually allows us to have a 201 gigabits per square inch. And so this promises that a bright future for the scaling of tape technology. This would lead to a 330 terabyte capacity per standard tape cartridge. And so they are so tape is actually a quite interesting technology because they have a roadmap that they have been following for until now, and that, as seen as with the vacuum sputter, is has the technology behind it to continue its impressive scaling. Today, we're at LOT8, and we have a raw capacity per cartridge around 21 terabytes. But we can see that at LOT12, which should come in a couple of years, they are advertising a capacity of 132 terabytes. And we know, thanks to the previous technologies, that there is still room for pushing that capacity further. And so, what's interesting about tape is that tape isn't the be all and end all for this technology, because we still have to build the infrastructure around it, and we have something that are called robotic tape libraries, where tapes would simply be sitting on a shelf, and you would have an optimized robot to select the tapes, to read the tapes, and to store the tapes once written. And so the infrastructure actually looks like this. You have your archives here with all your tapes, and then you have your robotic libraries that, when you request a tape, is actually going to come get the requested tape and then copy its data to an SSD that will then be um, used as the interface for exchanging your data with the outside world. And then for writing the data, you would get the data, you would store it temporarily into faster memory, and then that would be rewritten to a tape which would be stored forever, and you hope you'll never need to use it. So the takeaway from this technology and the previous section is that the perfect memory doesn't exist, and it's really just a question of compromise. And each application has its specific needs and its specific available resources to make that happen. And the goal is simply to choose the one that fits your application the best. Thank you very much. I hope you had a good time, and I hope to see you for our next session.